I'm thrilled to be speaking to you today. And I'm also delighted to know that there's going to be a really substantive Q&A session because I'm very much looking forward to getting the collective wisdom from this group and comments and feedback on this recent work. As Mikael pointed out, I am indeed going to talk about GRAND, guessing random additive noise decoding, hence the slight play on words about the grand irrelevance of code construction. Yes, because as we'll see, we know how to get rid of noise, but one has to have a code book first. This is joint work. All of the work is done jointly with Ken Duffy, who's the head of the Hamilton Institute in Maynooth University, Ireland. And all of the hardware work is done with Professor Yazicigil, who is a faculty at Boston University. So, we hear a lot about what is 5G. People, of course, working on 6G. And sometimes it helps to sort of look at all the plethora of really rich, interesting technologies and take a step back and try to say, what are we trying to do and what are we doing currently? And that's what I'm inviting, again, this group to do today, and to share with you some of my thoughts about, how to maybe change the way we approach the technology. So 5G, of course, formally is a set of standardized technologies, standardized by 3GPP, nominally standardized by ITU, but really post everything being set up by 3GPP. But informally, really, when people say 5G, 6G, I think what they mean is really a vision of ubiquitous communications integrated across technologies. You've heard me talk about the role of network coding in that, going back to what Mikael said about a lot of my work in that area, reliability and low delay. And reliability and low delay are two aspects that I'm really going to zero in today. Because, how do we get low delay for applications such as AR, VR, self-driving cars, anything where it's not just about rate, it's really about delay? How do we get that reliably? And this has led to the, the topic, which is maybe, not the most euphonious sounding, URLLC, ultra reliable low latency communications, but the topic of how to have reliability and low latency at the same time. So how do we get reliability? We get reliability by coding at the physical layer, adding redundancy, often with long codes. We'll talk about these long codes later in this talk. And of course, adding transport protocols. A lot of the work that I have presented in the past few years has been around adding network coding to substitute inefficient, slow transport protocols and make them faster and more reliable. But what I'm going to talk about today is the first part, the coding at the physical layer. Now, the problem is that the traditional modes of transport protocols and of coding at the physical layer actually are clashing with the low latency. The way that reliability is being provided usually is by either repetition after the delay of acknowledgement in the transport protocol, or at the physical layer by, in effect, averaging and taking an approach where you're converging to the mean. All right, so why are we doing that? Let's step back altogether and review the things that we all know. If you look at channel coding at a glance, suppose that I give you a binary string, say of 8 binary bits, and there's a problem in the channel, there's an error, and the last bit here turned from a 0 to a 1. Well, you hear this and you don't know what I said. You're trying to infer what I said from what you saw. If what you heard, which was this bit 1 at the end, was a correct possible message, then we're doomed, right? So if anything that I could have said was possible, we're doomed. It has to be that somehow you're able to infer two things. A, that this was wrong, that's what's called error detection. And B, after the error detection, that it was, you can try to infer with high probability what I actually meant to say. You say, well, it's likely that only 1 bit got flipped, and therefore what she meant to say is something that's only 1 bit away from what she said. And oh, lo and behold, there's only this one particular message which is possible. Okay, so of course, error detection is easier than error correction. And this is basically what we all know from coding theory. So what did Shannon do in 1948? Shannon said, okay, I can tell you basically how dense you can make your code book. So let's think of a code book as really being a dictionary, right? You see a word which is not a word that makes sense, which is not in your dictionary, and you search through your dictionary to see which word resembles the most the word that you heard. So in order to do that, you and I have to agree on a dictionary. Obviously, we would like the dictionary to have as many words, as many entries as possible. So the question is, the maximum number of entries here is 2 to the 8. What is the density of entries that we can have in a shared dictionary so that you still, with high probability, can make out the word that I said to you, even though there will be errors added to it? And so Shannon told us, we'll see in a slide or two what that density of code words can be. And, you know, there has been a huge amount of very technically involved, extremely mathematically sophisticated work around constructing code books and decoding. Okay, and we'll see why the code books and decoding, and really the decoding is a real part. We always think of coding and constructing code books, but really it's the decoding part that's the dominant factor. We'll see why that is. Okay. So this forward error correction, which we're going to cover again in schematic form, remember that what we would like now for as an engineering need is we would like to have a low delay. So we would like, of course, the words to be short. We would, of course, like to have low complexity. We would like to have low delay and low energy. Obviously, we would like to have flexibility because flexibility is desirable in order to have a highly responsive system. And of course, we would like to have robustness to the physical reality of correlated noise. And we'll see this at the end of the presentation, in particular things such as bursty noise. Now, the mathematical models that have come, you know, in a way that you can trace back, you know, if you were to do some sort of, you know, some sort of ascendance of the philosophy that we can trace back to Shannon has been really mostly around longer codes. That's to say, n, which is the length of the code generally, it goes large, so you have a limit so that randomness averages out. You have notions of capacity, which are concentration onto correct decoding when this n code length gets large. You have code constructions that are generally constrained in length and rate. We'll see why, because again, the decoding constraints. And there's really a very specific, sorry, is there a question? And there is a very specific pairing between the coding and the decoding. That's to say that you know, there is a decoder generally, a particular decoder is generally only fit for a particular code, sometimes even just for a particular rate of the code. You know, you can think of Reed Mueller with majority logic, Reed-Solomon codes with Burley-Camp-Massey, CRC-aided polar codes with CRC-aided successive cancellation list decoding, low density pair check codes with belief propagation. Again, you know, with variations, you can use belief propagation in some other aspects and so on, but by and large, you have to build a decoder with a particular code in mind. Okay, so let's go back to what I meant about this rate, about this density of the dictionary that you and I share in order to be able to talk to each other in a way with high probability, allowing us to correct errors. So the way that he looked at the number of entries in the dictionary is he looked at it in an exponential fashion. So he said there's 2 to the n possible strings. In a little example that I gave you, n was 8. And he said the total number of words I'm going to define as 2 to the n r, where rate r is in effect would be 1 if I had absolutely no error correction capability. So this is when we think of density, it's a density in the exponent, and that's what this rate r density means. Okay, so if I have a rate 4/5, then that means that 20% of the bits that I'm transmitting are being devoted really for the purpose of redundancy for error correction purposes. Okay, so Shannon identified the maximum rate at which communication could take place, and he said the following: if I have a binary, just to simplify the notation, I'm just going to think of a binary channel. All of this can, of course, very readily be extended to non-binary settings. The highest rate is 1 minus the entropy of the noise, which I'm just going to call H. Okay. And he also told us a way of doing this. This is what he said. He said, this is what you're going to have. You're going to have your code words. Remember, there's 2 to the n/r of them. And you're going to have all the strings of length n, again, binary. So let's think of 2 to the n possible strings. I have a bag with 2 to the n possible strings. And I have in a row on a shelf all of my possible code words. What I'm going to do is I'm going to take the first code word. I'm going to put my hand in the bag, pull something out, and assign that particular length n string, which I pulled out of the bag, to the first word. I'm going to call that my code word, the code word that goes with that word, with that message. I'm going to record that assignment. I'm going to put the string back in the bag, and then I'm going to take the second message from my shelf, go back in the bag, assign it, and so on and so forth. Okay, here in the northeast of the United States, there's something called a Yankee swap, where actually people go in a bag and grab Christmas presents. We're not doing that right now because of COVID, but I like to think of making these assignments as a Yankee swap in that you're making to randomly assign these items. Okay, so there's 2 different, and then what does the receiver do? You've recorded all of these assignments, and you copy that recording. You give a copy of that, and that is your code book. That is your dictionary. You give a copy to the receiver, and then the receiver looks at whatever it received, which we generally denote by Y, the output, and then goes through this dictionary and tries to find which one is the most resembles which of the entries in the dictionary the most resembles the Y that was observed. Okay, and that's this maximum likelihood is actually a maximum a posteriori probability, but because of reasonable assumptions about having done some uniformization of the messages through source coding, maximum likelihood and maximum a posteriori actually are the same. All the code words are assumed to have the same probability, again with good reasons from an engineering and theoretical point of view. Okay, so why don't we do what Shannon told us could be done to get this rate? There's 2 reasons. The first difficulty is the following, is one of storage. So let's say that this n is large. Remember, actually, the original idea is that you're doing a convergence to the mean, and therefore to get convergence to the mean, you use these large n's. Okay, of course, you'd like the R to be as large as possible. We'll see later that in typical communications, such as terrestrial communications like 5G and the such, you could the capacity could readily be 0.9 and above. So if my R is large, so close to 1, of course, we want it to be as close to 1 as possible for efficiency, and my n was large, say around 1,000 bits, which is not uncharacteristic, then what we're going to have is that 2 to the n/r is very, very large. So the first part, which is that recording of my, message to code word exercise, would have a huge number of entries. That would be a huge set of data that I would have to share as a sender to the receiver. So storage is the first one. The second one is computation. Remember that the receiver would then look through the code book, would basically look through the dictionary and try to match which of the entries look the most like the Y that was received. Okay, so there's storage and computation. So as a result, and I already mentioned some of the codes before, we have this massive evolution of codes. And, I like to put all codes here. These are mostly codes for erasure coding. Okay. Now, erasure coding, there are some for error correction. Erasure coding is super simple to decode. Okay. I know that people are still looking into it, but erasure coding, all you need to do is just Gaussian elimination. So, right. So we agree erasure decoding is trivial. And indeed, as Mikael pointed out, I've done a lot of work in tech transfer in network coding. And so there's a company in Denmark, Steinwolf, which does an amazing job with its software. It was a company I co-founded. And we can, decode on the fly erasure codes by doing clever things with the Gaussian elimination. So I'm not going to be talking about the erasure decoding because that's easy. Okay. So what I'm really talking about is these other codes, which are error correcting. Okay. So we have these block codes. Convolutional codes are basically really block codes, but defined over polynomials in the 1950s, 1960s, with basically some limits on the rate. Something called the cutoff rate is the de facto limit on those codes. We have so-called modern codes. I put them in the 90s, and I'm putting modern in quotation marks because low density parity check codes are considered modern codes, but of course they were created by my PhD advisor, Bob Gallagher, as part of his PhD thesis in the early 60s, late 50s. So they're not modern. They were rediscovered later, but they're not modern. These are basically pseudo-random codes. In 2009, Erdal Arakan, also a student of Bob Gallagher, came up with the first provably capacity achieving structured code, polar codes. It's actually interesting if you read his beautiful article, which appeared in JSAC when I was editor-in-chief, as Mikael pointed out. He actually connected that to his long-standing interest in convolutional codes, because as I mentioned, convolutional block codes were really de facto limited to going up to the cutoff rate. And his approach to developing polar codes was to take the cutoff rate and increase that quantity. Okay. So this is basically, these two difficulties have been, in effect, the storage and the complexity of decoding have been really the reason behind the evolution of all these codes. Well, not quite. As I told you earlier in the talk, it's really about the decoding. Okay, why? Because actually, I don't need to do that complicated register of the message to the code word. Okay, we know since the 1960s, 1970s that linear codes can be used to do this also in a capacity achieving way. All I need to store is a generator matrix, which will take the message as a string of bits and create a longer string of bits by multiplying that initial string of bits, which is the message, by a generator matrix to get a larger string of bits. And we know that these are capacity achieving. So random linear codes are actually capacity achieving. I'm putting these in these lighter spheres to show that these are in effect the darker spheres are the practically used ones, and the lighter spheres are the lighter used, the theoretically used ones. Okay, and so I'm separating the theory here from the actual practice. So okay. So what are we doing and why? So we know that really the reason why we're doing any of this code construction and decoder construction is actually not because of the difficulty of creating good codes. It's because of the difficulty of decoding them, right? We know how to create capacity achieving codes. The reason for creating non-random ones or more complicated ones is because of the decoders. Now, generally, if you look at the codes that we use, they're high redundancy, okay, which means that we're wasting a huge amount of bandwidth. We'll go into that later, okay, and they always have code-specific decoders. So again, what are we doing and why? We're making the engineering look like the available math, okay? What does it mean? I told you before that, capacities in commonly used channel conditions are very high. So if you look at cellular comms, mobile communications, bit flip probabilities are very low. They generally 10 to minus 3 or so. If you look at sort of like Nokia LDPC decoders, they're shooting towards 10 to the minus 2, and that's when things are bad. If you look, and we'll see later at some numbers from chips, if you look at the usual measurements of in the chip literature for the decoders, they usually are operating at 10 to the minus 5 and below, right? So below tends to be more for, say, optics, but 10 to the minus 5. Why? Because that's actually a fairly common regime, right? So you're looking at the energy use in a typical regime. And of course, you do your code construction for a more challenged regime, okay? Whatever you want it to be, it is not, 10%, 20% loss, okay? The channel capacity is very high, is way above 90%. But if you look at, say, 3GPP, 5G new radio, you're looking at LDPCs, which are not only very long, many thousands of bits, but also have rates that are low. They barely ever break the 90%, and they're usually more around 50%. And of course, all the decoders are code specific. Sometimes the decoders are even specific, not just to a code, but to a particular rate of the code. Okay. So basically, how have we been trying to get ultra reliability without latency? Well, we have been adding spectrum. Okay, that's been the approach. And the idea is I need this low latency. I have these long, messy codes. I'm just going to bump up basically the sample rate. I'm just going to add a lot more spectrum. And you see this in the huge amount of spectrum that is being used in 5G. You can look at, for instance, in the US at the recent FCC auction around 2.5 gigahertz. I like to think of this as drinking coffee. Now, don't get me wrong. I drink coffee, and I drink a lot of coffee. But the idea the idea is that we're adding spectrum. We're just doing the same things we've been doing. We're just doing them faster and using a lot of energy faster by sampling at higher rates because we add more spectrum and using a lot more energy. So the low latency doesn't necessarily mean that we need a ton more throughput. Really, what it means is we need a ton less delay. Okay. So let's go back to making the engineering look like the available math. You have these code-specific decoders. And again, this is why we have, in effect, standards. I need to make sure that if I speak to you with a particular code, the receiver you have a decoder that's going to be able to interpret that. You and I have shared that dictionary. Now, we've seen the dictionary itself is trivial. It just needs to be a generator matrix. So it's not because of the size of the dictionary that we need to do this ahead of time. It's because of the difficulty of the decoder, because the decoder has to be a completely different algorithm right now for each and every code. Okay, so it's not because of the code. The code is trivial. It's just a matrix. It's because otherwise you wouldn't know how to decode it. Okay, so the justification that is based on the historical presumption, which I will show you no longer holds, that error correction really requires a specialized, complex decoder, highly tailored, bespoke in dedicated chips. As I mentioned before, CASC alpha, CA polar, Berlekamp massive, say for both Schroeder Hockenheim, etc., turbo decoders for turbo codes, whatever it is, each decoder is matched to a particular code, and therefore that has been the reason for the standardization of codes. So the conventional approach is we code data to avoid corruption by noise, and we have these code-specific decoders which are dedicated to hardware. So a BCH may have a Berlekamp massive, a polar would have a successive cancellation algorithm, say Reed-Muller. Sorry, is there a question? No? It would have a Reed-Muller, might have a majority logic. CRC, cyclic redundancy check codes, are generally used for error detection, but they actually have enough bits to do error correction. There's usually no error correcting code for them. Random linear codes, which I told you we know since the end of 60s, beginning of the 70s from Gallagher, are capacity achieving, have no decoder whatsoever. So we end up with a big pile of chips, each for each code book, sometimes one for the same code, sometimes multiple ones for the same code, but just different code books at different rates. And what I'm going to show you is we can do this all together by guessing random additive noise decoding. Again, this is work with Ken Duffy at the Hamilton Institute. So what we're going to do is we're going to make the math look like the engineering. We're not going to go to long codes just because we have these concentration to the mean results. And we are going to have a single chip that replaces this pile of chips. Okay, so see here our beautiful rainbow chip that can take any code. We will show you we can actually change the code on the fly and basically be able to decode any code. So how does GRAND work? Okay, so where did this 1 minus h that I mentioned to you before that Shannon told us about, where did it come from? All right, so I have length n bits. Let's make strings of bits, right? Again, let's stay in binary. So how many possibilities are there for the received bit string y of length n? Well, there's 2 to the n. Okay. And I told you that the number of possible transmissions of possible code words was 2 to the nr. That's the size of the number of entries in my dictionary. To the nr, sorry, to the nr, okay? So what I have is that I have 2 to the n possibilities, and I have 2 to the nr for my output, and I have 2 to the nr input possibilities. Okay, this is modulated. So this is not the C that we saw before. This is post-modulation, but it doesn't matter. That's just how the code book is, translated into the physical domain. And then I have noise, which if I have bit flips, like I showed you from the very beginning, would be modulo 2 addition. It would be XORing such that if there is no error, you XOR with a 0. And if there's an error, a bit flip from a 0 or 1 or 1 to a 0, you've XORed with a 1. Okay. So from, again, simple statistical arguments, whether you want to call it the asymptotic equipartition property, if you're an information theorist, or if you're just an undergrad who took one class of probability or statistics, this is actually just the weak law of large numbers. That's all you need, basically the weak law of large numbers. With high probability, there's 2 to the nh sequences of, most of the vast majority of the probability is included in a group of just 2 to the nh sequences of possible noises. Again, remember the noise is all zeros if there was no error, and a 1 in the sequence of the noise indicates that there's an error there in the binary domain. All right, so what do I need? I need 2 to the n, of course, to be greater than or equal to the number of possibilities for the code words times the number of possibilities for the noise, because if I'm able to recover the message, even though it's noisy, it means that I was able to recover the noise. Now, of course, I wasn't interested in the noise, but if I looked at y and I was able to recover x, that means that I was also able to recover n. That means that I need to have enough bits to describe the noise as well as enough bits to describe the actual transmitted signal. How many bits do I need with high probability to describe the noise? Well, it's in a set of 2 to the nh. I need really nh bits to describe the noise. In any case, what I need is that 2 to the n be larger than 2 to the nr, which is the number of possibilities for the message, of course, times 2 to the nh, which is with high probability the number of possibilities for the noise itself, okay? And that means that 1 has to be greater than or equal, if I just look at the exponents here, has to be greater than or equal to, to r plus h, okay? R plus h, which is y r has to be less than or equal to 1 minus h, which is the capacity. This is the upper bound, okay? Okay. So remember that even though we're interested in xn, it's equivalent for me to discover xn as it is for me to discover n. So 2 to the nr is big. What's 2 to the nh? Well, I told you that the bit flip probabilities are very low, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5. So the h is of the order of the bit flip probability. So even if my n is, say, 100, but my bit flip probability is, say, 10 to the minus 3, then 2 to the nh is actually order 1. So I'd be better off, rather than looking at the thing which is complicated, which is the set of messages, the very large dictionary and has a lot of things in it, I'd be better off looking at the thing that's not complicated, which is the noise. I'm not interested in it, but it's easy. So let me try to figure out the noise, and from figuring out the noise, then I'll figure out the xn, rather than trying to figure out the xn directly. Think of this as kind of working in the dual. How am I going to do that? I'm going to input yn, which is, of course, the observed signal, and a codebook membership test. That's to say, I'm only using my codebook as a hash, as a verification mechanism, okay? So I'm going to start by guessing the most likely noise, say all zeros, there was no noise. If after subtracting the effect of my putative noise, which I'm calling z of n, that's the guess of what the noise may have been, I indeed obtain something in the codebook, then I'm done. If I didn't obtain something in the codebook, then I start again. I go to the next most likely noise effect. I then try to subtract the noise effect. If that's in the codebook, I'm done, and I keep doing that until I have obtained something in the codebook, or until I give up, because actually, if I keep going after a while, it turns out you can abandon and still be capacity achieving. The math for that is a little bit more complicated, of course, than just the weak law of large numbers. You have to use a large deviation approach. But of course, what happens is that you are, of course, at some point running into an error, right? Because if what happened is that you've done a lot of guesses and you haven't hit a codebook element, it actually means that with very high likelihood you have an error. And by the way, it also means that you can often transmit above capacity for a while, because if your guess of the noise still gives you something inside the codebook, and with high probability, even though you are above capacity, you actually still got the correct decoding. So there's very interesting, not just error bounds, but actually success bounds that come out of our original work on Grant. Now, the nice thing about this is that this is a universal decoder, okay? The only way I'm using the code is, again, just as a hash, just as a verification. This is the only place where I'm using the codebook. I'm just using to see whether something's in a codebook or not. This is a function of the noise, basically of this NH, of how the noise operates, not of the code rate. And we'll see later, of course, that if my noise is not IID, then actually, of course, I can do my guesses in a more efficient manner in this setting. Okay. So this new approach is something that we have implemented in a chip. It was just presented this last fall at ESS-CIRC, which is the largest European circuits conference. It was one of a few papers selected as being longer papers in the conference. Again, this is actually very unusual for an academic paper. Most of these papers come from industry. So here's a picture of our chip, and we can do measurements. We fabricate in 40 nanometers. We get a lot of questions as to why we didn't go to 10 or 15 nanometers. 40 nanometers was what we had available. You basically have to end up piggybacking on a chip run, and that's what was available to us. But we're very proud of the fact that we still get really fantastic results, and in some cases, record results. For some metrics, record results, even in this technology. What codes do we have available? Well, of course, we can do all the codes that were out there, Reed Mueller, CRC-aided Polo codes. We can also do Reed-Solomon codes. We can also do random linear codes, which are available at every rate and every length. Of course, you can do things like puncturing, which is a bit of a dark art. Sometimes you can get code lengths in different rates, but by and large, by the way, here you see on the abscissa, the N is the code length and R is the available rate. Okay, so we can do them all. So we can do codes that were decodable already, such as BCH and Reed Mueller. You can see in thin lines, these are the theoretical results. In thick lines, these are the experimental results that read from the chips. Don't read too much into the difference in the waterfall curves. This is block error rates, so the error per code word against the log of the bit error rate, the -10 log of the bit error rate. Like I said, don't read too much into the curves because they have different rates. These are different codes at different rates. Okay, so we're able to do different lengths, as you can see here, different rates. And so we just, this is not about the performance of the codes. I'll tell you that about the performance of the codes. This is just to show that we can do all kinds of codes. We can also do codes that were never decodable before. RLCs, this is the first ever decoding of RLCs, but we can decode them with this chip. CRCs, Polo codes and CA Polo codes had soft decoders. This is a hard decoder. I'll talk later about soft decoders. There was no, to our knowledge, no hard decoding available for these codes. So on A, you see that we actually match or outperform. I haven't shown you how Burley-Camp Massey and others do on these, but we always, because we're maximum likelihood, we're optimum. So we always do at least as well as the state-of-the-art decoders. I'll show you later. In some cases, we do significantly better than the state-of-the-art. Okay. And we have very good performance. This is a comparison against the state of the art. I should say this last column here comes from a group at McGill University led by Warren Gross. Many of you may know him as the person who really spearheaded the adoption of CA Polo codes by creating the first chip-ready algorithms for CA Polo decoding. They have a synthesis. We have an actual chip, as I've mentioned. We are of course universal, I'd like to in particular highlight this part here, which is the latency. You can see that our per code word latency is lower than anybody else. Here's not recorded because of course there isn't an actual chip, so you can't have an actual recording. But here's our latency. You can see it's much lower, so we're very proud of that. Our energy or picojoules per bit right now is not the lowest; it's the second lowest. This was our first chip. Anybody who's done a chip knows that, after you send it for tape back, a few nights after that, you go, oh, geez, I should have. So we had a lot of, we should have, and we're incorporating this in the next chip we're creating. So we shall see, because of course the whole field is changing, but we expect to be able to have the world record in energy as well, not just in time. Okay, so by the way, what about soft decoding? So it's interesting. Particularly if you look at somewhat short codes, it turns out that actually using a hard decoder is better than the state-of-the-art CRC-aided successive cancellation with list decoding, even for large lists of size 16. Recall that actually the complexity of these decoders goes exponentially with the list size. And so a list size of 16 is actually quite high. It's higher than most chips. So we sometimes even just using hard decoding, with no information, soft information, because we're doing something optimal, is better than what people are doing right now. So, our chip is able to do better already than some of the state of the art, but there's still more to be had if we use soft decoding. This is ordered reliability bit decoding, which is a variant soft decoding with GRAND. So how do people do soft information? You know, it varies a lot. I'm just going to give you one example, which is, again, state of the art. You take the signal, demodulate it, you have some bits, usually say 3 to 5 bits of soft information per information bit. And the way, for instance, CA polar codes are decoded in the state of the art is that you create a list of possible decodings, and then you use a CRC, a cyclic redundancy check, in order to pick out of that list which of the decodings was actually correct. Okay. By the way, for us, what happens is a CRC aided code is just a linear code, you know, because you have the polar code, you have the interleaver. I'll talk about interleavers again later. And you have the CRC. You combine these three. It's just one linear code. The fact that, you know, they all had different purposes, we couldn't care less. It's just one linear code. And so we can decode it with our chip. But you can have soft information. GRAND only has soft information. We have shown how to do full soft information in SGRAND. So we showed that last year at ICC with our student Emmett Solomon, who recently graduated. And you can find nice approximations. One of them is order reliability bits that Ken showed at ICASP this year. So SGRAND, by the way, fully uses soft information, so produces truly soft ML decoding. It's very implementable in software, so certainly I would encourage anybody who's looking at decoders right now to use SGRAND as a comparison, because, and people in chips and are already doing that, because that is now the gold standard. This actually, you can find the ML decoder. So how do we do with this? Well, we can get a lot of different rates, just to give you an idea. So it's not about coding at low rates. It's not about coding it's not coding at high rates, it's not about coding at short codes. It's just this code rate. It's really about the total amount of redundancy that matters. So to give you some idea, you can see here with an SNR of a little less than 10 dB, or the random linear code if you use OrbGrand. So the SNR of about 10 dB gives you a bit flip probability of about 10 to the minus 3. I can see the different rates and block lengths that you can get. Okay. And this is what you can see. So this is why I'm talking about the grand irrelevance of codebook construction. Here's the polar codes using successive cancellation. This is using OrbGrand. Okay, and you can see that they are basically about the same, of course, because we're optimum and successive cancellation is good. You can see that, you know, even though its capacity achievement is not necessarily that fantastic in terms of block error rate. Here's EB over N0, which is a measure of the energy per bit over the spectral density of the noise. So this is basically, if you will, how much energy I'm devoted per bit, normalized by the energy of the noise. And so I'm just going to do a quick time check here on my computer. Okay, great. More minutes. So what you can see is that we see that if we use, these are CRCs of 11 and 24. This is because that's what the 5G new radio 3GPP standard has with polar codes. So we see that we do very well with OrbGrand. And as a matter of fact, these are all at the same rate. They're all the same. The only one that doesn't do so well is polar codes without CRC. That's the only one that doesn't do so well. You can see here that in the case of 24 bits of CRC, we do quite a bit better than, again, the state of the art with list size of 16, which is somewhat higher than the state of the art chips. Some of them can go up to 32, but you know, they don't work well at that rate because they have huge energy use. But actually, what I'd like to point out to you is what happens if I use just a CRC. It does as well as the polar codes with CRC. So it's really not the code, it's a decoder. A CRC code does great, a linear random code does great. As a matter of fact, I'd like to point you to some recent results, not from our group, but a group more again on the circuit side, at TU Eindhoven. They just did a lovely, this is the group of Professor Batsira Stimming. They just did a lovely study where they compared encoders and decoders built using state-of-the-art machine learning schemes, and instead using random codes chosen with just a little bit of, a little bit of smarts, with a few constraints, and using GRAND. And they showed that GRAND always either match or outperform using machine learning techniques. Okay, so this also indicates that, the large effort right now in looking at machine learning for code construction and decoders is probably not needed. If you do the decoding correctly, we have a maximum likelihood decoder. And it turns out, which again goes back to Shannon's original idea and back to Gallagher's idea from the 60s and 70s, random linear codes with, some constraints. You don't want to do something, overtly stupid, like choose a whole bunch of zeros in there, are actually very good. CRCs, you have to be a little careful, but a huge number of CRCs are fantastic. All of these do very, very well. Really, you don't need to be putting a lot of effort into your code construction. And, we see the same thing here. Okay. Now, the last thing I wanted to get to, which I mentioned at the beginning, was sort of being able to be robust to the realities of noise. And, here's some measurements from the literature on the noise before interleaving, and what do we do? We interleave to make the noise look ID. But actually, if we took into account that the noise is not ID, if we took into account the correlation of the noise, I mentioned to you when I presented the GRAND algorithm, this would be beneficial, because then actually you could guess more, any structure there is in the noise, any even traces of correlation will actually be useful in terms of being able to guess the noise more quickly. In particular, you may be able to decode way beyond the minimum distance. The minimum distance is often treated as being an essential, if you will, a fundamental property, but it's not. It's just a consequence of assuming an ID noise. So here, if you look at, in this particular case, a CRCA-ed polar code, again, this is one that's compatible with 5G NR. What do you have? You have that, if you do full interleaving, you have a binary symmetric channel. This is CA-SCL with AWGN. And if you use grand Markov order, which, by the way, this doesn't have soft information. This is so we're comparing soft information for the state of the art with, we just have hard information. We don't even have soft information. And what you can see is that we have huge gains. Okay, we have gains of over 60 dB. The more bursty the channel, the better we do. But on top of that, we have a huge gain in delay. If you look at the standard IEEE interleaver, it's interleaving, we have lengths of over 100. So you're getting a gain in delay of over 100. You're getting a gain in EB over N0 of over 60 dB with just using an off-the-shelf decoder, just by doing the decoding properly. Okay, so you have a huge power factor and a delay factor. You've gained 100%. You gain a factor of 10 of 100, which right now, remember, we would have to do by adding a whole lot of bandwidth, right? We would have to basically buy 100 times more bandwidth from the FCC and pay a lot of money for it. So with that, I will open to questions. Hope of course, we should continue to drink coffee. I'm definitely going to, but we should use GRAND. We should do smart things faster and with less energy. Thank you very much.